Okay, so let's take a look at these examples here. So if we look at this first one here, g of x is the absolute value of x plus 3. A couple of things I have to decide. I have to decide what is the original function, what is the basic function that we're starting with, all right? And that's going to be the absolute value of x. And then we're going to see what are we doing to it. So what we're doing is we're adding something, we're adding a number, a quantity, to the whole previous function. So immediately I know if I'm doing something to the whole previous function, it's a vertical effect, and if I'm just adding something to it, it's a vertical shift, and since it's positive, it's up. So let me graph on this, let me sketch absolute value of x on this. So that would just be that characteristic V shape here. All right, that's the absolute value of x. All right, so what we're saying now is what we're going to do is shift this graph up by 3. So here's 1, 2, 3. So that point that was at the origin before moves up here, and everything else stays the same in shape. Okay, so that would be the absolute value of x plus 3. All right, so right here I'm doing it all on one set of axes. In the future, when we do more transformations, I'm going to use separate axes to show each transformation so it doesn't get too confusing on one graph. But since we're only making one movement here, it's okay to do it on one graph. All right, so now let's look at this one and see how it's different. Again, I can see that the basic function I'm using is absolute value of x. But instead of adding something to the whole previous function, I've added it directly to the x. All right, that means it's going to be a horizontal effect. And since I've added directly to the x, that means I'm going to shift to the left. So I'm still starting with the same basic function, and this is what I have to know what these functions look like. So that's the absolute value of x. But this time, I'm going to go back 2 to get to -2 here, and that's now where that corner point is going to be. So the rest of the shape stays exactly the same. And that would be the absolute value of x plus 2 directly on the x. All right. Now here we'll do 2 different actions, and we will keep them on the same axis for the time being. All right. So when I look at this, I see inside here that the basic function I'm looking at is the square root of x. So in a little while, we'll go through exactly how to figure out what order you should do these transformations in. But for now, let's think basically we're going to start from the x and work out. So the first thing that happens is I do this -3 directly on the x. All right. So let's take a minute and step back. So the first I'm going to start with is just the basic square root of x graph. All right. So the next thing I'm going to do is I'm going to do what this -3 directly to the x. Since it's directly to the x, it's got to be a horizontal. And since I'm subtracting 3 directly from the x, that means it's going to have to shift to the right 3. So let's go 1, 2, 3. And so I'm going to have the same thing, the same graph, but just shifted to the right. So here we're getting the square root of x minus 3. Right. Next, what I'm going to do is now I'm going to apply this -2. But realize that -2 is -2 on the whole previous function. So maybe it's easier if we set out a little game plan here. We started with the square root of x, then we moved to the square root of x minus 3, and then we're going to move to the square root of x minus 3 minus 2. So the big difference here is, in this first step, from here to here, realize that the modification was just made on the x. But now if we consider this our new function, square root of x minus 3, when we go this way for this next step, that minus 2 is made on the whole previous function, not just the x value. So that's why this is turning out to be a shift down by 2. So we're going to go down 1, 2, and that's where this key point, this sort of anchor point, is now going to be. So now the shape is still the same, it's just been shifted down 2. So this is square root of x minus 3 minus 2. All right, so we see the big difference between applying it to the x itself or applying it to the whole previous function. Okay, so remember though, in both of these examples, we were adding or subtracting a number from something. What happens if we multiply? All right, so multiplying is going to be stretching and compressing of the function. All right, so I'm going to go through some of this detail here, and it seems a lot to remember. And the key is that you won't have to remember this exactly. If you get an idea of what's happening, you can recreate it without knowing all this for c greater than this or c less than this stuff. But let me introduce it that way. All right, so first thing I'm going to do is vertical stretching and compressing. So the idea is if it's vertical, we must be doing something to the entire previous function. So we're saying that our new function, g of x, is some c times the whole previous f of x function. So we're multiplying the whole function by c. So now, when you multiply, there's a big difference between multiplying a number bigger than 1 and multiplying a number smaller than 1. Because bigger than 1 makes it bigger, and smaller than 1 makes it smaller, so that's going to have a big difference here. So if we multiply the function by a c that's bigger than 1, it's going to stretch the graph of f of x vertically. Now, if instead we multiplied by a c value that's less than 1 but greater than 0, we certainly don't want to multiply by 0, because that'll wipe out the function, and we're not talking negatives yet. That'll be a separate thing. So if we multiply by a number between 0 and 1, that's going to compress the graph, shrink it vertically towards the x-axis. So what might this look like? So imagine we had a graph of a function that just looked like this. We're just serving it as a picture right now, so it doesn't matter what function it refers to. But this is our original f of x right there. So if we multiply by a c value that's bigger than 1, what it's going to do is actually stretch this thing vertically away from the x-axis. So something like this. It's still anchored at the same points. The other way, it gets stretched down away. All right, so this is c f of x, where c is greater than 1. Now, on the other hand, if we did a c that was between 0 and 1, it would shrink it towards the x-axis, compress it. So we would get something more like this. Okay, so this one here is also c f of x, but when c is between 0 and 1. All right, let's see this in some examples. So g of x is 2x squared. Obviously, basic function here is x squared, so we start with that. All right, just the x squared function. And then I want to know what's going to happen when I multiply by 2. All right, so there's two ways to think about this. I'm multiplying by a number bigger than 1. So, oops, I'm sorry. I should have started with the dotted version to be consistent with what I was doing before. So this is x squared. All right, so I'm multiplying by something bigger than 1, so it should stretch this vertically. Sometimes it may not be clear what that means. So if we want to do something to show us, we could just pick a point from the original function. So if I put x into the original x squared, I'm going to get 1. So I'm going to get that point 1, 1, because that's what x squared has on it. Now think 2x squared. If I take that same 1 value and I put 1 into 2x squared, I'm going to get 2, meaning that point is actually going to be here, showing me that what's happened is these points have gotten stretched up, so everything should happen in a similar manner. So that's how I know I get this tighter function for 2x squared, which makes sense because it's like stretching the x squared up, which is going to tighten it. So that's a good idea of how you can use point values to show you what's going on. In a similar way, let's say we did 1/3 x squared. Now again, it's still based off x squared, but now we're multiplying by 1/3. So let me get the basic x squared function. And now what we're going to do is we're going to multiply by 1/3. So if I took that same 1 point that went to 1 before, now when I put 1 into this new 1/3 x squared function, I'm actually going to get 1/3 as a result. So the point is there. So everything has been compressed down. So I get something that's more like this, that's wider. All right, so that's how I've gotten what happened when I multiplied by a number between 0 and 1. So again, we can use those test points there, I think of them as, to show us how the graph has moved.